I've been asked to do a little explanation about how to calculate flow rate from a velocity profile in a flow of a Newtonian fluid. To sort out how velocity and flow rate are related, we can consider first a simple problem of a flow where the velocity is uniform, meaning it's the same everywhere, so we have a constant velocity. And we imagine that flow going through a cross-sectional area of a simple shape, let's say a square of area 2 centimeters squared, for example. So let's choose a value for the velocity. Let's choose 4 centimeters per second. And we're asking, what is the volumetric flow rate through this cross-sectional area? We can figure that out by thinking about how much fluid would pass through the area in a time, let's say 3 seconds. So in 3 seconds, there's fluid passing here at 4 centimeters per second. In 3 seconds, the fluid would pass through, and a volume of fluid would have passed through that is the equivalent of this rectangular parallelepiped. So the fluid is traveling at 4 centimeters per second. So over a time 3 seconds, this fluid would have gone a distance 4 centimeters per second times 3 seconds, or it would have gone 12 centimeters. Now we know the fluid has gone 12 centimeters, so we can calculate the total volume that has passed through this surface we've chosen by calculating the volume of the parallelepiped. So the volume is equal to the height, which is 12 centimeters, times the cross-sectional area of the base, which is 2 centimeters. And if we want the volumetric flow rate, we want that volume that has passed in the time we chose. So we divide that by the time, which was 3 seconds. So the speed of the flow times the cross-section area divided by the time gives us 8, this is centimeters squared, 8 centimeters cubed per second is our volumetric flow rate. So having done this example with numbers, we can now figure out what the overall general formula is. And what we did was we took the cross-sectional area, A, and we multiplied it by this height, which was the equivalent of velocity times time. So we get our general formula. The volumetric flow rate is velocity. This was time in the denominator as well, so the time cancels, times cross-sectional area. This case of constant velocity is not always the case. We know, for instance, in our flow down an inclined plane that the velocity varies with position. And we can adapt our situation to the case where the velocity varies. Let's imagine again we have this cross-sectional area. It's a square looking at in perspective. But now we're going to have the velocity vary with position in some way. So in order to take into account all these variations in velocity, we need to divide our cross-sectional area into little pieces over which the velocity is constant. And then it becomes the previous problem. So we have this velocity as a function of position. And now we just add up the contributions in each of these 9 squares, for instance. So if I just do that same sort of a logic and say, oh, in some amount of time I will have created this rectangular parallelepiped of fluid, I know I can calculate the velocity of the volumetric flow rate due to this location as the velocity at that location times the cross-sectional area. If I want the total volumetric flow rate, I have to add up all the VAs. And in this case, there are 9 of them, so I'll say it's the summation, I equals 1 to 9, of the velocity at each individual square times its area, and I get the total flow rate. If I have an unusually shaped cross-sectional area and a variable flow, then I again divide it up into these little squares, which I might call the differential area dA, and I add up, integrals are summations, I add up over that cross-sectional area the variable, let's say varying in the x and y directions, the variable velocity v. I have to integrate this over the limits of the area, whatever they happen to be. So this is our more general equation for the volumetric flow rate as a function of the cross-sectional area and the velocity field that's presenting to the cross-sectional area. We can make this a bit more solid by considering a real example. So let's consider the example we're studying in class, which was flow down an inclined plane. So this is a problem where we've solved it completely for the velocity field in class, and we have a fluid, a Newtonian fluid, flowing steadily down an incline. And the velocity varies in the x direction and is not a function of the y or the z direction. So this is exactly the case we just talked about. There's a cross section here, and that cross section is a wide slot of fluid. The height of that fluid is h, and the width is some length here in the width direction, the y direction, which we can call w. So this is the area across which we must add up all these little velocities, and these velocities vary in the x direction. Okay, so this is still my x direction, and this is my y direction. So now I'm going to use my formula. The flow rate is equal to the integral over this cross-sectional area of the velocity, which in our case is a function of just x, and it's the z component of velocity, but it's going to vary in the x and the y directions. X varies from 0 to h, from 0 to h, and y varies from 0 to some width value, w. So this is the integral that we must carry out. So to carry it out, we just copy that equation. Q equals the integral from 0 to w, integral from 0 to h, of vz of x dx dy. And we include now the velocity profile, which was a whole bunch of constants, which I'll call a, times h squared minus x squared dx dy. We first carry out the y integration. Nothing is a function of y. So we get a h squared minus x squared times y, evaluated from 0 to w. This inside quantity becomes a h squared minus x squared times w minus 0. And so now we have to carry out 0 to h, a w h squared minus x squared dx. And this is a simple integral as well. And we'll move the a and the w on the outside. The integral of this with respect to x is h squared x minus x to the third over 3. And we evaluate from 0 to h. And we get a w h to the third over 3, putting the x here, h in for x, minus, h to the third, putting the h in for x, minus h to the third over 3, minus 0 minus 0. And so we get a w 2/3 h cubed. Putting the a back in from the original problem, we get rho g cos beta over 2 mu w times 2 times h to the third over 3. And that's our final answer.